draft book by Professor Andrew Ng of Stanford University, Machine Learning Technical Strategy for AI Engineers in the Era of Deep Learning. This book is available free of charge online and also with an open license that you can communicate with anybody without violating any copyrights. With some of the references from, again, Professor Andrew's course on deep learning available on Coursera. And some of the slides are from Tom Mitchell's book on machine learning. So I'm grateful to all these people from whom I have derived most of the material. As some of the participants are from, I was told, subjects other than computer science, I'll quickly spend 2-3 minutes on the resources, as these resources are well known to the computer science community, but may not be so well known to the community outside of computer science. So the field of machine learning today is easier to learn than ever because of the availability of a large number of online courses that are available. This slide I created about 2-3 years ago when there were a few courses on machine learning and deep learning. Today, if you do a search on Coursera.org, you find a large number of courses, and these are highly specialized courses. So the first course is the machine learning course that was probably the first MOOC, one of the 3 MOOCs that Stanford University gave, one in machine learning, another in database systems, and the third in artificial intelligence. Way back in 2011. This is followed by a course on machine learning specialization from the University of Washington, which teaches basics of regression, classification, and clustering. And there is a sequence of courses on deep learning, 5 modules from Professor Andrew. And it's important for the computer science community to learn what goes behind these algorithms. So there are courses like mathematics for machine learning. This is a complete module of 3 courses from Imperial College London. And these days, as the machine learning is being used extensively, it also exposes the lot of personal data of the people. So there are issues of ethics that become important. So there are specialized courses on ethics in the age of artificial intelligence. This is an advanced module or a group of courses from the National Research University of Higher School of Economics in USSR. And they teach a lot of serious stuff like how to win competitions on Kaggle. Google is the developer of TensorFlow, and this is a specialization from Google itself. Now, these organizations are partnering with others like IBM, Google, and others in the industry to develop a lot of fruitful courses. This is another platform which is very popular in the computer science community, edX, edx.org, which was an initiative from the Harvard and MIT. So why I have put this slide is because of the specialized courses for our colleagues. Like there is a first course that appears is tiny machine learning. We have been applying machine learning for a lot of tasks. Now this is how we can apply when we are dealing with these small devices like handheld devices or mobile phones or IoT and things like that. Then there are courses for colleagues in finance, which specialize in finance. This is from New York University. This this is a sequence of courses from Amazon. So you can see whatever courses you can do. Quantum machine learning is a more serious course for the physicists may be interested in this particular course, and because it tells how quantum physics has been used from in building quantum computer, which are still in progress, and also in certain family of algorithms, so-called quantum-inspired algorithms that were not known hitherto. So that means they have a probabilistic framework. These algorithms are designed in probabilistic framework, even though they run on the deterministic systems, our standard computing machines. So with this, we are back to the topic of our talk. Although these neurons were invented way back in 1943, that was the time that the first computers like ENIAC was being built, which was completed in 1946. And there have been a lot of developments. We are not going through those historical developments. And in 80s, when Professor Hinton and colleague developed this fast algorithm for backpropagation. All the backpropagation algorithm was developed by Verbos 1975. These systems become more and more popular because the speed matters in the machine learning tasks. And subsequently, there are a lot of developments in deep learning techniques, which some of the, I think, speakers have spoken or will be speaking about. And what these developments have helped us with is that they have improved the computer architecture so that machines are becoming fast and fast. Also, they have the side effect that the technologies which could not work earlier, they have been now working, more research has taken place in those fields. This is one of the earliest examples of success with neural networks. Alvin, why I'm showing this is that this is a simple model based on a 32 by 32 very coarse images, which was trained for about half an hour of driving, fixing some cameras on top. And as you can see, this is a 30 by 32 by 32 image being fed to simply 4 hidden units. And there are 30 output units. It's on the right-hand side, the unit indicates right turn. The left-hand side, it indicates a left turn, and in between, small variations to adjust the vehicle. All right. So the scale drives the scale of computation, scale of the availability of data, drives the success in machine learning. And this is a curve which is showing that in the initial days, we have very little data, and consequently, we are limited by the performance. Nowadays, we have a lot more data, and the performance is much higher. So for the introduction, now we come to the core topic of today's talk, that is how to train the machine learning algorithms. While dealing with the machine learning algorithms, we need to set up our data sets. Typically, the data set is divided into 3 parts. A training set, which is used for initial learning. Then a development set called dev set for short, also called holdout cross-validation sort. Holdout cross-validation set is used for parameter tuning. And finally, we have test set, which the algorithm has not seen during the training and development phases, where we evaluate the performance of the algorithm on the kind of data that it is likely to see when it is going to be put in practice. All machine learning algorithms work on the basic assumption that the development set and the test set, they come from the same distribution. although we'll look at some variations also. Choose the dev set and test set data. That is, they should truly reflect the kind of data that the algorithm is going to see in future. And that is the kind of data on which you want your algorithm to do well on. So in this talk, we largely focus on one example. Say that we want to launch a mobile app which distinguishes a cat from a non-cat image. Now, we have not yet launched the app, so we do not have any user data. So we are unable to get the data that accurately reflects what you have to do well on in future. In the previous slide, we said that choose the test and dev set data to reflect the data you expect to get in the future and want the algorithm to do well on. Now we are saying we do not have any such data available to us. Now the question I'm asking is, what is that we can do under this scenario? How to proceed? Will somebody like to suggest something, please? I'm sure you can give some. No answer is no wrong answer, by the way, because we are all learning in the first place. And also, we are also learning from the responses, because every response has a reason. And we investigate that and see that how that response, how effective that is, or how more effective that can be, and so on. So please give some suggestions. Any suggestions? I hope you got the problem. See, the problem is we want to launch an app. What is the purpose of this app? The purpose of this app is to distinguish a cat image from a non-cat image. So when a user uploads an image, the app should tell, is it a cat or it's not a cat? So the trouble is we do not have any such real data which is available to us. So what should we do about how to get the data? What is the first step? Because I think you should participate so that our discussion is more meaningful, you know. Of course, I can present the slides, but that may not carry much meaning. Yes, please. Okay, we can give some images. So we have got some very good answers. That one answer says that we can collect data from the internet. Surely we can collect a lot of data. And whenever today we are in any difficulty, so we always look for internet to collect some data. And then someone is suggesting we can give some images, or probably one is trying to say one can shoot some images or ask our friends to do so. That's a wonderful idea. If you don't have a resource, what is the best we can do? We ask someone else to help us. So some friends can click the images and they could be useful, and feed cat images ourselves for training. Very good. We can use Google image search. We can do, that's right, or internet images. Someone said, I think it's a similar answer. So while internet is a great source of information, so there could be some subtle differences also, in the sense that mm, mm, that the data characteristics for the internet images, it could happen that most of these images are very good images, whereas the images which the users are uploading, many of them may be internet images, but a lot of images could also be the user taken images. So they may not have been taken in very good lighting conditions, or mobile may be shaking, or something else may be happening, or maybe the mobile camera is not very good. These days, most of the mobile cameras are very good. So if we do not have a resource, and if we cannot get down to the real life scenario, then the only thing we can do is that we try to approximate the real life scenario. And our friends have given very nice answers that once the ad is launched, we could subsequently we could update our dev set and test set using actual user data, and then we could enrich, we could refine our algorithms even better. All right. I have another question. We have a classifier, let's say cat versus non-cat, or for some other purpose. We have a classifier which has 90% accuracy. There is another classifier which has 90.1% accuracy. The question we are asking is, should we distinguish between these two classifiers? All right. Since this is a Boolean question, there can only be two answers, yes or no. So people have tried to reason out that, and some people have argued that of course we should, and some people are also saying that based upon the application, and we could take a decision. I think that makes a lot of sense. Will somebody like to say that what kind of application should we distinguish and what kind of application should we not distinguish? Can someone throw more light on that? Yes, please. I hope getting the question. The question somebody has answered that based on the application and the data set, you would like to answer yes or no. You don't want to answer just like a random answer. That's, I think, very nice way of approaching the problem. So the question is that what kind of application will it be useful? See, if you are having an application where, say, you are doing a web search, you have a search engine, you want to compete with another search engine, then even a 0.01% accuracy might matter. It's not just 0.1%. And okay, let's say we decide that we want to carry out this kind of improvement. We want to increase the accuracy from 90% to 90.1%. Obviously, the answer will have to come out of your experiments. So you have a training set, you have a development set, you have a test set. So what should be the size of a development set? If you want 90.1% accuracy, is it okay to have a size of 100 or 1,000 or 10,000 or 100,000 or 1,000,000? What is reasonable size for this kind of an experiment to be conducted? Can you help us, please?
Sir, please you scroll down your chat.
Okay. This can help. Oh yeah, I'm looking for this. Okay, I think there are a lot of answers and good answers. Right. Someone has written at least 1,000. Surely it cannot be less than 1,000. But even 1,000 is a little, or rather on the lower side, because see, if you have 1,000 examples, right? And if you expect to see 90% accuracy, 90% accuracy would mean you have 900 correct and 100 are wrong. Are you following, please? 90% accuracy would mean you have 900 are correct and only 100 are wrong. So out of these 100, you have only, out of the 10% wrong, the accuracy is increasing only by 0.1%. So by 0.1% would mean how much? You don't expect really, one example here and one example there. That could be just a chance occurrence. You will not really be able to see whether it is because of the performance of your machine learning algorithm or it is just a chance occurrence. So at least you would require some 10,000 kind of an examples so that you hope to see. If you see, this is given 10,000 examples. If you remove the 2 zeros from the right, what you get is 100. And if you remove one more zero, then you get you are at 0.1 level. That means you expect to see a difference of 10. So you will be able to judge that, okay, fine, from 9,000, you are moving to say 9,010 at least, or 9,008 or 9 or 11 or 12, something like that, so that there is some distinguishable appearance. And we will not be able to distinguish one here and one there. And that could more likely be because of chance rather than the performance of the algorithm. So you can see that, please, when we are dealing with finer distinctions, why I have put this slide over here is just to illustrate that when we want accuracy, which increases in very fine terms of the level of 0.1%, then to evaluate this kind of accuracy, we require huge amount of data, at least 10,000 strong data. All right. Another related question is that how should the training, test, and dev set should be distributed? Historically, we used to deal like 70% of the data in the training set, some 20% of the data in the development set, and then a little data, say 10% of the data in the test set. Over a period of time, the size of the data have really increased. Now we deal in millions of data. There's online applications for this face recognition. These have been tested on millions of images. So when you are dealing with such huge quantity of data, then most of the data is pushed into the training data so that your algorithm is a lot of learning capability. Why do you push a lot of data into the training? Because the training algorithm has to learn a large number of parameters. So if you have a lot of data, then training algorithm will learn the parameters well. And when I say a lot of parameters could mean millions of parameters. These modern neural networks, convolutional networks, and all these networks, they have millions of parameters. And 1% of the data may be pushed into training and through the dev set, 1% into test set, or even half each. Okay. This is a standard matrix for evaluating the classifiers. We are considering the same example, cat versus cat. Then when the top, you see the true class, and on the left-hand side, you see the predicted class. So what this matrix means is the following, that when an example is a cat and we predict it as cat, we call it true positive. When example is a cat and we predict it as non-cat, we say it's false negative. It's a positive example of cat, but we are reporting it as non-cat. Then if there is a non-cat image, but we are reporting it, the algorithm is reporting it as positive, it's reporting as cat. So this is, we say, false positive. Falsely reporting that image is a cat. And finally, we have the true negatives. Image is not a cat, and we're reporting it as non-cat. Okay. All right. little terminology over here. Terms like recall, specificity, precision, and accuracy. Recall refers to how many positive examples we are predicting as positive. That's what we say, true positives. How many we are predicting as positives divided by true positive plus false negative means they are actually belonging to the positive class, but we are reporting them as negative, false negative. Then we have precision. Your true positives, and we want to have an assessment of the number of positive instances versus the number of reported positive examples. For example, if you go to a lab and ask whether I have COVID or I don't have COVID, and lab declares everyone has COVID. So your recall rate is very high, true positive. And there's no false negative because you are reporting everyone as positive. So true positive by all true positives divided by all true positive, it's 100%. But your precision is low because you are reporting a lot of false positives as positives. What is a false positive? Actually, the patient doesn't have COVID, but we are reporting it as COVID. So the precision is low. Or we say that specificity is low, that true negatives. It is actually, there is an example which is a negative example. Then we want to evaluate vis-a-vis all negative examples. How many negatives you are reporting out of all the negative examples. And lastly, we have a simple measure of accuracy, all true positives or true negative divided by all the examples. Okay. So there is a classifier A, which has 95% precision and say 90% recall. There is another classifier which has 98% precision, but 85% recall. That means this performs better in terms of precision. The classifier B performs better in terms of precision, whereas the classifier A performs better in terms of recall. Now the question is, which classifier should we choose? It's a hard question. Obviously, there is no simple answer to this kind of questions because, again, that could depend on the application. And dealing with multiple criteria could be difficult for most of the people. So one tries to define some kind of aggregated measure. So given the precision and recall, we compute the F1 score based on these measures. And we find that the F1 score for the first classifier is 92%, and for the second one is 91%. So you typically prefer. So why do you compute the F1 score? Because it is an aggregated measure which balances between the two measures, say precision and recall. This is another example that you are tracking the accuracy of your CAT classifier in 4 key markets: US, China, India, and others. This gives 4 metrics naturally. Again, how to evaluate the performance? The performance will be evaluated as some kind of an average or weighted average, or maybe you want to try in the Asian market, then you will give higher weightage to China and India, or maybe you want to launch the application only in US to begin with, then you might give higher weightage to US market, and so on. So you'll have to find out some kind of weighted criteria so that it is easy to interpret. Although a lot of medical applications, we cannot afford to ignore the precision recall dilemma. And both are important, and the doctors would like to see that you have at least a threshold precision and a threshold recall rate before approving a test. So you might compute an F score, but that F score will be considered valid only if you do a threshold on both the measures. Sometimes it is possible to have multiple criteria, but they are not equally important. For example, if you see these classifiers here, A, B, C, classifier A and B have accuracy 95% and 97%, and they take running time of 80 millisecond and 90 millisecond. Then we have another classifier which gives you an accuracy of 99%, but takes 2000 milliseconds. Oftentimes, so one of the metrics could be considered as satisfying metric. That means it is okay if we perform reasonably well on that, it is fine. So we are not being too fussy. Most of the applications, 80 milliseconds and 90 milliseconds will not make a difference. So one could prefer the one which gives the higher accuracy. All right. Back to the same example of a CAT application. We have observed that the app is accurate to the extent of 90%. However, this app makes mistakes and it classifies certain dogs for cats. So what you did was that you took out sample of 100 misclassified development examples, you count what fraction of these are dogs, and you found that 5% of the misclassified images are dogs. Now what do we do? We want to improve the accuracy of the classifier. What is the task at hand? The task at hand is we want to improve the accuracy of our classifier. So can you suggest something, please? Okay. Yes, please. Any other suggestions quickly? It says that. Someone says resampling. fine tuning. I think fine tuning means fine tuning the parameters of the algorithm. Okay. Okay. All right. Now, so you have applied a lot of mind to this problem. If I were in that situation, I will not do that. And I think many of you will also not do that. Whenever we have a problem, what is the first thing we do is we look for the internet. I'm getting 5%. I'm getting some dogs being classified as cats. I'll do what to do. When you do a Google search, you find a tool. That's a great tool. What it does, they claim to identify all dogs. And this tool has a price, say maybe 50,000 rupees or 1 lakh rupees, something like that. Now, the question I'm asking is, will you consider buying this tool and integrating with your application so that you get rid of all these examples? I hope the question is clear. We found a tool on the internet. Someone has given a very nice answer. Depends on the data size. What kind of data size? Yes. Ansari ji, what is your take on data size? What kind of data size do you need to decide the matter? So, someone says you have to fix the problem. And someone is suggesting that I'll prefer to do it manually to save money. See, manually will not probably work here because these are the errors. Because user is going to upload an image. And when the images are being uploaded, and it is at the runtime that you find out that it's going wrong. So what we need to do is we need to do something probably with, if we want to do something with the algorithm, or to put the question other way around, if we have really good tool and we really trust this tool that it will remove 100% of the dogs, okay? It will remove 100% of the dogs so that there is no incorrectly reported dog where dog is being reported as cat. How much do we expect the accuracy to go up? Right now we are at 90%. 5% of the misclassified images are dogs. We have purchased a tool, okay? That tool removes all such errors. Now, what is the result we are expecting at this cost? We certainly expect an improvement. Let's see how much improvement. See, all misclassified dogs marked as non-cat. Done. This is the best you can do. You cannot do anything better than that. Suppose you have a sample size of 100. In a sample size of 100, how many errors do we expect to see? We expect to see 10 errors. Out of all the errors, 5% are dogs classified as cats. So 5% of the errors, not 5% of the total number of samples. We are right now we are dealing only with 5% of the errors. So there are 10 errors out of 100. There are 10 errors. So 5% of 10. 5% of 10 would be half. So accuracy will move up from 90% to 90.5%. I hope this is fine with everyone. So important point is we need to evaluate that what is the effect of our action. Okay, let's see another example. Suppose we find that 50% of the misclassified images are dogs. Then what is the best we can expect? So most of the people are answering 95%, so I'll go with the majority. Now we have 50% of 10. 50% of the misclassified images are dog. Out of 100, there are 10 errors. 50% of 10 is 5. So accuracy moves from 90% to 95%. Someone has written 94.5% and probably may not be trusting the tool 100%, so might have written 94.5%. But as I said, we believe the tool that it will do a 100% job. All right. Let's consider one more example. So we have our classifier is giving us an overall accuracy of 90%. That means 10% overall errors. And the mislabeled data is about 6%. Based on a sample study, we found that 6% data are mislabeled. So the question we are asking is, should we correct the labels in the dev set or let it go? Yes, please. What do you say? So some people are saying that it is a correctable error, so we should correct it. And we should correct in the dev set itself. Surely we can do these corrections. And let us evaluate the effect of these corrections. Now, again, please, 90 out of 100, 90 correct, 10 wrong. And 6% of the data is mislabeled. This applies to all data, including the erroneous data. So that means whatever errors we are getting, 6% of those errors might have been contributed by the erroneous labeling. So 6% of 10 would be 0.6%. That means our accuracy would go up from 90% to 90.6%. That's fine, that's an achievement. But probably if you want your accuracy to be 95% or 97%, then this is not the primary cause. This mislabeled examples are there, but they do not constitute the primary cause of error. Why? Out of 10, 9.4 errors are due to other causes. 9.4 out of 10 means 94% of the errors are due to other reasons. So let us fix up the major problems, then we will see what to do with this. Okay. All right. Now, suppose we have reached an overall accuracy of 98%. That means 2% overall errors. Errors due to mislabeled examples, 0.6% out of overall 2%. So 0.6 out of 2 is now 30%. Errors due to other reasons is 1.4%. So now this mislabeling is contributing 30% of the error. So to answer the question, should we correct the mislabeled examples? So now it could be more logical. Yeah. Right. I have a question here. In the previous slide, see, we were doing error due to mislabeled example, 0.6, 10% accuracy, 10% error. Sorry, 90% accuracy, 10% error. Now, we said that since the mislabeled data is 6%, so 6% of 10 is 0.6%. And therefore, we rejected the idea of correcting the labels. In the next slide, we are saying 0.6% out of overall 2%. Why we are not computing 0.6% of 2%? Previously, in the previous slide, we computed 6% of 10. Now, why we are not computing 6% of 2? Are you following, please? In the previous slide, we said 10% overall errors. Okay, 6% due to mislabeled data, 6% of 10, we got the answer 0.6. Now we are saying 2% overall errors. So we are not, we have changed the style of calculating. Should we not have done 0.6 into 2 by 100? 0.6 into 2. Six percent of 10. So 2% of 2% of 2 would be how much? 0.04. Are you following, please? Yes. Correct. I think so. Mayank Singh ji is reporting that earlier on we had 6% were the mislabeled examples. 6% of the mislabeled example out of all these errors. Then 0.6% we got this number by taking 6% of 10. Now we have continued with the same example. We have not changed the data set. Data characteristics have remained the same. So the mistakes which were there because of the mislabeling, they could not have been corrected as a result of refinement. What you have done, you have probably learned better features. Probably you have got a better classification technique that is helping us to improve certain mistakes. But the mistakes that were there because of the mislabeling, they cannot be corrected. So those mistakes must still be there in the data. It is possible that one or two mistake may be here or there, because since the processes have changed, the algorithm has changed, so there could be little bit difference. But by and large, all those errors would still stay. Therefore, when we are computing here, we are taking 0.6 out of 2.
उसके अलावा जो फाइनेंशियल एनालिसिस की नॉलेज वो उस लास्ट के 2 सेम में दे रहे हैं, वो तो एमबी में भी हम नहीं देते.
So 0.6
बीटेक डेटा एनालिसिस मतलब बीटेक इन डेटा एनालिटिक्स ऑसम सिलेबस बना है.
So 0.6 out of 2 will be 30%. I hope this is fine. So errors due to other causes are 1.4% and 0.6% due to the mislabeling. So now 30% of the errors are due to mislabeling. So this could be significant. Now, important thing to understand here is that whatever process you apply for fixing the dev set labels, remember to apply it to the test set also, because otherwise what will happen is your dev set and test set will come from 2 different distributions. Our analysis will not be proper. Okay. Now, what about the labels of the examples that system correctly classified? Do we need to examine these also? The answer is simple in this case, that both the original labels and the one generated by the learning algorithm could be wrong. And you know that two wrongs can make a right. So it is possible that there was a cat and we mislabeled it as non-cat. And our algorithm reported cat as non-cat. Now, a non-cat is matching the non-cat. Even though algorithm is wrongly reporting, but it is appearing to be correct answer only because the label is wrong. So if we fix only the labels of the examples that the system had misclassified, we might introduce a bias into the evaluation process, which might overrate the algorithm. All right. In continuation of the discussion, it is common when we get into problem, we get some errors, then like cat versus non-cat, then we want to manually look at the images, see what's going wrong, and so on. So this is called the test which you reserve for physically examining. This is called the eyeball deficit versus the black box deficit, which you don't care to examine manually. So suppose you have 5,000 examples in the dev set. Error rate is 20%. 20% out of 5,000 will be 1,000 examples. And we want to examine some 100 errors. 100 errors means 10% of the errors we want to examine manually. So the question is, what should be the size of the dev set? If you want to examine 10% of the error, you will probably look at the 10% of the dev set, and 10% of 5,000 will be 500 examples. So size of our dev set, eyeball dev set will be 500. Size of our black box dev set will be about 4,500 examples. So as a general rule, examining about 50 errors gives a good sense of the error sources. Examining about 100 errors gives a very good sense of the error sources. Okay. Looking for 5% error rate, looking for 100, sorry. If n is now 5,000 and the error rate is 5%, previously error rate was 20%. Now, if the error rate comes down to 5%, notice please our task becomes much more higher, difficult. Because n into 5 by 100 is now 100. So which gives the number of examples as 2,000. How many examples we should have? N is the number of examples in the dev set. The question we are asking is, how many examples we should have? 5% of which, right? How many errors are there? 5%. How many errors we want to see? 5% error means we want to see for about 100 errors. To see 100 errors, we have to find out n into 5 by 100 is 100. So n should be 2,000. So lower the classifier's error rate, the larger your eyeball dev set needs to be in order to get a large enough set of errors to analyze. So notice please, this is not an easy task. This is a difficult task. And if you have already achieved significant progress in your machine learning task, it is still more difficult because you will have to really struggle to examine and find out the causes of errors. So notice please, this example just illustrates how much manual effort these people do who are designing the machine learning algorithms. Because we tend to believe sometimes that the algorithm is doing everything, and they are automatically fine-tuning everything, and fantastic results are coming. Fantastic results are coming, but there is a lot of manual effort that goes behind this. This is a standard slide which is showing the relationship between bias and variance. This is an example of a classifier. The blue line indicates a classifier. And if you look at this classifier, you can see that the first classifier shows there are a lot of errors. Here is a case of high bias. The second classifier is just right. There are some mislabeled examples. And the third example is a case of a classifier which is overfitting, so which does not leave any scope for generalization. We will discuss these with some examples. Suppose we have a classifier which has 95% accuracy. I'm sorry, we want to design a classifier with 95% accuracy. That is our objective. And the training set error is 15%. When we test it on the dev set, we are getting 16% error. So we say that the bias is 15%. Error on the training data is called the bias. And the difference of the error in the training data and the development set data is called the variance. Now, question we are asking is, what is that we can do under such circumstances? Are you following the question, please? The question is, we want 95% accuracy. That's the objective that we have in mind. We find that training error is 15%. When we tested on dev set, we found it's not doing significantly bad, 16%. So we want to improve the accuracy of this classifier. So what is that we can do about this in this kind of a problem? So I think that's, now that you have learned machine learning, a lot of algorithms about machine learning, so you may be able to answer that some suggestion, and all suggestions are good because they have some merits, and no suggestion will probably have all merit only. Someone has asked a question about the difference between bias and variance. The 15% error on the training data, we say it is the bias of the algorithm. 16% error on the dev set. So how much more is the error on dev set? It is 1%. It's 1% larger than the error on the training set. So we say that variance is 1%. So difference between the bias and the variance, correctly mentioned by someone. Difference between the training error is 16. I'm sorry, training error is 15%, dev error is 16%. So difference between the two is 1%. So that is what the variance is. Can you please suggest something? And there is not one, there are many things that you can do. Yes, please. At least one answer. Hello. Things that you can do here, and probably your algorithm is not working well, you know. If you have 15% error, that means something is wrong with your algorithm. So we need to do something on the algorithm. It may be that you have not, it's a case of, yes, it is a case of underfitting. No doubt it is a case of underfitting. Yeah. Someone is suggesting we do cross-validation, and probably cross-validation is not going to help us in reducing the error, because we have 15% error. So, and since we have drawn these from the same distribution, it's unlikely that picking another set of data will help you out in this situation. Probably we have to do something more serious about the algorithm. It may be that you need to fine-tune the parameters, hyperparameters. Maybe you want to change the number of neurons in a layer. Maybe you want to increase the number of layers to make the model more complex. Maybe your model is very simple model you are using. No? You are using simple logistic regression classifier, and you have so many features, and that it simply doesn't work out. So you need to have a model which is more complex. It may be that, you want to have features, maybe you're running a support vector machine, and your support vector machine is not able to handle thousands of features. So maybe you want to have more distinctive features. You want to do a better feature selection, or maybe you want to apply principal component analysis to get aggregated features. And maybe you've done a lot of regularization, so you can reduce the regularization. Or can we increase the size of data? Will it help us? Yes, please. Someone is saying not in the given case. Adding more data is really not likely to help us, because the algorithm is already stuck up. Algorithm is already not able to deal with the present data. So adding more data is something that's not going to help us in this particular case. And someone is saying that we should reduce the dimension, we should do principal component analysis that we are discussing. We can also use the wavelet transform. We can also use some other form of transform. And lastly, I've written do nothing. Could do nothing be a brilliant idea sometime? Of course, you can always decide not to do anything. But could there be a situation that do nothing is a brilliant idea? Well, there could be some cases and where the algorithm probably has reached its best, even with 15% errors. For example, if you're doing a speech processing application, speech to text, and if you find that you have reached a stage where if you look at the erroneous audio clips, you find that even with repeated listening, you can't make out what the speaker is saying. And the algorithm is also not able to make out what it is saying. So then it could be okay, fine, if, that in many cases, so the human performance could be a yardstick for the algorithm that, okay, if we have, or there could be an optimal error rate. This is what we call optimal error rate. If we have somehow reached the optimal error rate, or if we find that images are so blurry, 15% images are so blurry, that the light condition is so bad, or they are taken from such large distance that we cannot figure out what it is. You know the correct label because you know what was the object there. But the image is taken from such a large distance that there's no way to tell whether it is a cat or what it is. So obviously you can't put the blame on the algorithm. So this is what we were discussing. Or there's something called ideal error rate. I think we have discussed it already. So the bias can be redefined now as unavoidable bias plus avoidable bias. What is the unavoidable bias? The 14% of the clips are too noisy. So if the error is 15%, we'll say that 14% is unavoidable and 1% is avoidable. Of course, human performance is not good on all tasks. Can you give some example, please, where human performance is not good, or the machine learning performance exceeds the human performance? Can you give some example of application? Someone has written a floating operation. I don't know. What is a floating operation, please? Yeah, okay. Floating number computation is right, that the machine performs much faster. That's okay. But I think we are not discussing, although that's correct, but that we are not discussing that as of now, because right now we are just discussing a simple task of a classification kind of a task, and we are looking at the performance, or maybe regression task, or some machine learning task whose performance we want to evaluate vis-a-vis humans. There are many applications, please. For example, like predicting that which movie you will like. There is no way I can give a correct answer, or there's no way even your good friend can answer whether you like a particular movie or you will dislike that, unless you have a very close friend with whom you have been often going for a movie and you have been discussing together before and after watching that what kind of movie it is. So the person knows what kind of genre you like, what kind of actors you like, what kind of music you like, what kind of story you like, what kind of action play you like. And then one can probably say that whether you will like a movie or you will dislike a movie. But most of the cases, your friends will not be able to help you with which movie you should go to watch. Whereas it is very easy for a machine. Machine learning algorithm can quickly ask you to tell some movies that you have liked in the past. And if you fill up some movies that you liked and didn't like, machine can build up features. The machine learning algorithm will build up features on what kind of stuff you like, what kind of stuff you did not like, in what combination you liked or disliked, and thus give you a better performance. If you ask someone how much time it will take you, I'm in Delhi, I don't know how predictable the traffic is in Aligarh, but in Delhi, if you have to move, say from Pitampura to South Delhi or to Connaught Place, there is no way one can give you an accurate estimate of how much time it will take. And if you're going sometime around 10 o'clock or 11 o'clock, all one can say is that you might take 45 minutes to 1.5 hour time, depending on which day, depending on so many factors that will be there, which you don't know how they are operating today and now. However, the machine learning algorithm can quickly compile the data for last few days and also have a look at the traffic conditions. As of now, of course, there may be an accident between the time you started off and the time you reached, and that might disturb your plans. But normally, if you ask Google how much time it is going to take, Google gives reasonably accurate estimates within plus minus, say, 5 minutes on several routes and plus minus 20 minutes on most of the routes, almost all routes.
Hello, sir.
Yes, sir.
May I request you to please conclude the session because last 15 minutes are reserved for question and answers.
Okay, okay. So we'll just conclude the session. So we have already discussed this. In the first case, we see the training error is 1% and development error is 11%. What does this mean? What it means is that training error is very little. And we are getting an error on the dev set. That means probably you have overfitted the parameters. So what you need to do is probably you need to relax the model. And in the second case, we have already discussed 15%, 16%. Third case, we have 15% training error, 30% error. That means the algorithm is not performing well anywhere. It's a case of high bias and high variance. And the last example seems to be okay. This is the kind of situation you would like to happen. So as a general remark, when we have high avoidable bias, what we do is increase the size of the model, try different architecture, modify input features, reduce regularization. What typically doesn't work is more training data. As opposed to this, when there is a high variance, probably it might help you to add more data to the training set, apply regularization. I think we don't have time to discuss that. Basically, what regularization means is essentially somehow reduce the weights or reduce the size of the model by dropping out certain features in certain runs. Or maybe we stop early. Maybe I have a slide here. So you have a model like this. So as you're training, the model is become better and better and better. This is plotting the loss. Loss means how much off you are from the solution. Then you find the error starts increasing. So when the error starts increasing, you would like to stop here. So this is, although the error is reducing on the training data as you continue, but on the dev set data, the error is increasing. So you may be happy with this much error on the training data rather than bringing it to close to zero, so that overall the model is performing better. And decrease the size of the model, modify the input features based on insights that you have got from the error analysis. And you need to modify the model architecture. Probably you prefer a simple architecture. Don't make it further complex, make it simple. So that should be fine. I think we can stop over here then. And so I'll be happy to answer any questions.
Participants, any question from your side? Actually, sir, you were discussing during the session and you are answering their questions. You respond their questions during the session, so they don't have they don't have questions.
Okay.
I have one, because we receive one question. Difference between dev set and validation set.
Pardon?
The difference between dev set and validation sets.
Okay. Basically, so we use these terms interchangeably, dev set and validation set, and test set is kept separate. So we have three terms: training set, dev set, and validation set we use interchangeably. And then test set is one data which the algorithm has never seen during the training phase or the development phase. Dev set means we want to validate after the training has been done. And why we are reserving the test set separately? Because if we use it oftentimes, then that data will also be exposed to the algorithm, and the algorithm will never be looking at independent data, and when we will run it actually in the field, you will get a lot of errors because you have trained the data on these data sets, but the examples which are being seen in the field are quite, or at least somewhat different from those.
So we have another question.
Yes, please.
Is dev set is necessary for all kind application to improve the accuracy?
I'm sorry, is it?
Is dev set is necessary for all kind of applications to improve the accuracy?
See, what is the accuracy? Accuracy basically means that true positive plus true negatives, we should report cat as cat and non-cat as non-cat, right? So how many cat as cat and non-cat as non-cat you have reported divided by the total number of examples that the algorithm has seen. So this is the accuracy. Now, the question is how to improve the accuracy. If we only see it on the training data, and that means the algorithm has been trained on certain data, so it has fitted to the characteristics of the data. We have not evaluated its generalization ability. We need to check how this algorithm will perform on the unseen data. And this unseen data is the dev set data, or to be more precise, call it midway unseen data. So this dev set data is very necessary, therefore. See, if we don't have enough data at all, then of course you have to have two sets, the training and test. There's nothing better that you can do. But oftentimes we'll have reasonable data, which we can split into three parts: training, dev, and test. So dev set data helps us to evaluate the performance of the algorithm on the data on which it has not been trained. Algorithm has not been trained.
Okay, sir. So we have one more question.
Yes, sir.
How to decide number of cross validations?
You are asking for k-fold cross validation?
So just I'm reading the question. So it is how to decide number of cross validations from Dr. Ajmer Singh.
Yeah, probably what it means is that when we are doing that k-fold cross validation, how to decide the number of folds. When the data is less, we typically do 5-fold cross validation. But if we have more data, then typically one does a 10-fold cross validation, reserving every time 10% of the data. The basic idea is that you are building multiple models. And since we are building multiple models, what does it mean? It helps us to understand that the algorithm, the machine learning algorithm that we have developed or that we have fine-tuned, it has not given us good result just by chance, that 90% was in one set, 10% is in the evaluation set. So it is not that by chance those 10% gave good result. Rather, the algorithm has enough strength that any portion of the data could be used as training data and other portion can be used as test data. So that gives us a confidence regarding the stability of the machine learning algorithm. And finally, what we do, once we get a reasonable confidence, and then the product has to go into the market, then once we are confident of everything, then we can finally run the training on the 100% of the data and to send it to the market.
So we have one more question.
Yes, please.
So if we have two types of data, one independent and one dependent, what should be the method of training data having their values as pixel locations?
One dependent, another is independent. Please, I'm not getting this. Dependent and independent. What is the notion of dependent and independent? Can you, Mr. Kulvaibhav ji, can you please clarify? What do you mean by dependent and independent data? Dependent on what? Independent of what?
Yes, sir. Sir, if
I'm sorry.
So
I think if people mute themselves, I'll be able to hear better. Just one person can speak.
Okay. Hello, sir. Hello.
Just Kulvaibhav ji, please.
Yeah, yes, please. Kulvaibhav ji, yes.
Yes, sir. If we want, yes, sir. Yes, sir. Sir, if temperature is a dependent and vegetation is independent, like we are trying to predict temperature with the help of vegetation, because we assumes that in our algorithm that vegetation is not that fastly moving. being constant.
Okay.
On other hand, the temperature is a more dynamic phenomenon on surface. So temperature is dependent on vegetation. So we are taking its temperature as dependent and vegetation is independent data.
Okay, got it.
So and their
I got
values
your point.
are at in a
Essentially,
pixel location.
yeah, I think you are asking a different problem. The problem we were discussing just now was a classification problem. I think what you are referring to is a regression problem. That give
Exactly, sir. Yes, sir.
in the regression problem, we have some independent variables, and there is a dependent variable, and there could be one or more dependent variables which depend on the whose outcome depends on the independent variables. So in such a situation, I think we can randomize the entire data. We can randomize the entire data and then pick up, reserve some samples for evaluation and the others for the training of the model.
So any other question from participant? Sir, there are no more questions, so that is stop here.
Okay, thank you so much. And I'm really impressed.
Thank you so much, sir. Here is Dr. Faisal Anwar, one of the coordinator of this course. And it was very informative session, sir. And participants have really learned a lot here. So we will try to meet in physical mode as well, sir. And if all will in this current scenario, we are not able to meet physically, but in future, sir, we will try to organize some other FDP in physical mode. So we will request you to please visit our department as well, sir.
Okay. Thank you so much. I'm really impressed, and such an interesting audience asking good questions. And I think Mayank Singh ji has written his question is unanswered. That what do you do during the development phase that we miss out while training? So the answer is very simple here. The development phase does not come after the testing phase. Development phase comes before the testing phase. To tell in simple words, previously we used to do training and testing, just two things. So when you do training and testing, the problem with this approach is that the algorithm has already seen the test data, and the parameters are being fine-tuned in response to test data. Therefore, this test data gets bound to the learning process. And subsequently, when we evaluate the performance on the test data, we are not able to get really independent responses, because when we see the data in the practice, we find that the algorithm does not perform as well as predicted. Why? Because the test data was actually being used for the training also in this particular case. How it was used for training? First we did training, then we did testing, we found there are errors, and then in response to that, the algorithm learned again, then we again tested. So what we are doing? So it is as if that's also part of test training data. We are evaluating the performance on this to train the model. See, the model is being trained, including the test data as part of it. So therefore, the people started with test data being completely independent, that the algorithm will not see at all. Till what time it will not see? Till such time that you are almost 100% confident that it is doing well on the training and the development data. When the performance on the development data has really reached your expectation level, then we will see the test lab data and I'm sorry, try to evaluate its performance. And we hope When we do that, the performance will be good. If it is not good, then we'll try to figure out what's happening, what are the differences, and probably the culprit may not be the algorithm. Culprit may be the data characteristics. Characteristics of the data which is there in the test set may be different from the characteristics of the data which is there in the dev set or in the training set. So that is why it is very important we say that the characteristics of the dev set and the test set should be same. So Mayank Singh ji, I don't know whether I have answered your question or. Hello?
Yes, Mayank Singh ji, are you there?
Mayank Singh ji is here? Okay.
So he has written in chat box. Thank you.
Okay. Thank you so much. And it has been really great pleasure interacting with you.
Thank you, sir.
Thank you so much.
Sir, dear participants, now all of you can leave.